Working. All right. Hi and welcome everybody. Thank you so much for attending my talk about data visualization literacy. Gone virtual is kind of an obscure title. I'm aware of that, but I hope it's going to make sense by the end of the talk. I'm a PhD student here in town. As I said earlier, I had a very short walk here, which was amazing. It was beautiful this morning here. Yeah. This is going to be the outline of my talk. I'm going to talk about two projects we did here in our lab using virtual reality for two very different application domains, one being architecture and one being biomedical visualization. Then I'm going to talk a little bit at the end about data visualization literacy as kind of the theoretical framework behind what we are doing. I'm going to want to ask a few questions at the end about immersive data visualizations. You can actually see two kind of teasers, previews of the projects I want to talk about. So project number one, about visualizing the 3D structure in Laddie Hall art. Laddie Hall is a still brand new building here on campus. It houses the School of Engineering, which I'm a part of. It was opened in January 2018. And then in April 2018, we got this. This is an interactive art piece called Amatria. Since you're here in town, I highly recommend that you go to Laddie Hall and check it out. It's maybe a 5-minute walk from here. Amatria is suspended from the ceiling. It is built out of hundreds of thousands of individual parts, glass with colorful fluids in it, dozens of sensors, little speakers, hundreds of vibration motors and lights to create kind of an interactive, almost jungle-like experience. You can also see that we have a scaffold structure here made out of hundreds of acrylic pieces that have been thermoformed. It's really hard to put in words. You have to see it for yourself. It's really close to you. So as you can see, Amatria is visited by a huge amount of people and a very diverse set of people. Here on the top left, I saw a bunch of people from Cook Medical. We have public tours on a semi-regular basis. This is IU President Michael McRobbie and the First Lady of IU. And this was my most favorite tour I ever gave the space to a bunch of middle schoolers. They would not stop asking questions, and it made me really happy. It was a really cool experience. So here you can see that Amatria is actually very front and center of the building. This is up on the 4th floor. So you come here up those stairs to go to your office or to any of these working rooms, and then she's right there. She's also very audible throughout the whole building. Now, this is what Amatria's electronics scheme looks like. You can see that we have hundreds of these little vibration motors. We have also several dozen of these lights. We have a huge electronic backbone made up of individual Raspberry Pis. This in itself is already a work of art to me, this electronic schematic. It is all controlled by a control laptop in a control closet off to the side of a room. And now the challenge is the makers of Amatria are based in Toronto. So the question that we were asking was, how can we enhance Amatria maintenance workflow with VR? So I want to give an intro to the problem. This is Mark. Mark is a great guy. He's one of the architects of Amatria. Mark's studio, however, is in Toronto. It's actually exactly at this address, which is a 9-hour drive away from Bloomington, which makes maintenance in person very hard and very expensive. So when Mark was here the last time, we started to prototype a virtual reality visualization. You can see the first draft here on that screen. This is actually the very first draft. This is what Amatria was originally supposed to look like. You can see that it looks very different now. So the idea was to take the 3D model that the studio had already developed and just port it into a VR experience. So what we did was, you can see this here. This is going to be a video. We can see Amatria hanging up here. You can see that we used a simplified 3D model because putting in the full Rhino 3D model crashed Unity pretty much immediately. So we have this very simplified scaffold here, and we have a colorful overlay of all of the electronics in the sculpture. So you can see that we have sensors and actuators. Actuators being lights and speakers and anything that does something, emits some kind of reaction. Then we have those colorfully overlaid over the scaffold. You're going to see here that you can also turn parts of the data overlay on and off. Now, the reason why you see this "you are here" message and those gestures up here is that we used this VR application and actually ported it to a kiosk. We thought we put so much work into making the 3D visualization work, we have to make it useful for visitors as well, not just for the architects behind the sculpture. So for Amatria's first birthday, back in April, we gifted her this touchscreen kiosk that is now deployed under the sculpture, and it's running the visualization I just showed you. And it actually allows visitors to understand the 3D structure of Amatria a little bit better. This is obviously a work of art, so it comes with a certain kind of shroud of mystery that we don't want to explain away. But we believe that using three-dimensional visualization with an easily accessible touch interface is going to make the experience of this art piece richer. Another very neat thing that we were able to implement was real-time data input. This is a piece of Amatria called the Sound Sensor Scout, and this is its virtual representation. And you're going to see here in a second that my hand is going to come into this infrared sensor. And the closer I get through a real-time data feed, the more excited this particle system gets. Here we go. So this way, visitors can actually stand in front of the sculpture, get close to it, and then see their reaction in the data that we visualize. For many people, this is like their first interaction with a real-time data visualization. And since the sculpture is actually lighting up as you get closer to it, you have this real feeling that it is something living in front of you. So we try to kind of enhance this experience with a living but not living thing through data visualization. Good. Now, the second project that I would like to talk about, which is very, very different, is about tissue registration. So our lab here at IU is part of the Human Biomolecular Atlas Program, or HubMap, by NIH. The goal of this 7 to 8 year project is to create a 3D map of the human body at the molecular level, which is incredibly high res. It's basically a Google Maps of the human body, if you so will. So our lab is involved in 2 very specific pieces for this, and I'm going to have images to that in a second. One, there's a lot of acronyms in this project. The Common Coordinate Framework Exploration User Interface, or CCF-EUI, and the Registration UI. And I'm going to show you what those are here in just a second. So one part of having a Google Maps, or having a fully explorable map of the human body, is to actually have an interface to do that. So this is the CCF Exploration User Interface. As it currently is, obviously this changes every 3 months with every milestone we have to deliver. So this is a clickable map of the human body. Right now, we only have data for the kidney. The heart is going to be added next. And then after that, hopefully the spleen and the liver. I don't have any background in biology, so it is like truly interdisciplinary. We were in Stanford just a couple of weeks ago for the big annual meeting, and it's challenging. I haven't really done biology since high school, so in this exploration user interface, you click on an organ, let's say the kidney, and then on the kidney you have this overlay down here. And it tells you how much data is in there. And you click on it, and then you can actually get to this biomolecular view, because some information about the patient. And then finally, you get to this high resolution view where you can actually zoom in and out. This is the Google Maps aspect, right? And then you can actually go ahead and you have a list of ontology terms down here. For example, show me the outer cortex and the inner cortex. I cannot explain to you what those are, but they're part of the kidney. And then you can actually see this kind of blue overlay here. This plays a little warning. I'm going to show some images of human kidneys here in a few slides, just so you know. So as you can see, this is just the user interface to explore a collection of data that is already there. So the data has to get into the system somehow. This is actually the core task of HubMap, is to find an infrastructure to actually get human kidney heart data from a surgery table into this application, into this exploration user interface. So the second piece that we are building is the registration user interface. And for that, we were asking, how can we make it easier for users of our system to register organ data? When I talk about users of our system, I speak about surgeons. So this is how it's currently done. This is a human kidney on a paper printout with some lines here and centimeters and some scales. And this is how currently organs are being registered. They're basically put onto paper and photographed, and then they put that onto presentation slides and just highlight the areas that they're going to cut out. So they take the whole kidney and then they take certain sections out. Then they basically type in all of these values by hand into their metadata systems. And so I'm going to have some more images here. This is going to be important in a second. So when you cut up a kidney, obviously this kidney is not very healthy. If you cut up a human kidney, you cut out sections of it, usually kind of like in a concentric circles going around the side of the kidney here. And we thought there must be a way to make this easier, rather than having to put them onto a piece of paper and then manually writing out at what position you take the cut out. So we developed the registration user interface, which we can see here. So you can actually see an animated GIF of how it actually works. This is currently deployed to a website. We have a representation of a kidney here. This is a left kidney of a male patient. We have an interface over here that allows us to control this little sample tissue here. So basically, you type in your tissue sample size, you can rotate it, and then you can move it simply with your mouse into the position where you want to position it. Now, the important part for me as a PhD student was, how can we make this 3D interaction as easy as possible for a user? Most people have no experience working with three-dimensional objects, let alone aligning three-dimensional objects on a two-dimensional space. So what we did is we restricted the user's ability to interact with the system to 2 dimensions at a time. You can see that we are using orthographic camera projection, so we don't really have any depth perception. And in this view, the front view, the user can only move the tissue slice on the X and Y axis. Okay, so we kind of like willfully restrict the freedom of the user to make it easier for them to actually place the tissue sample. And then you can click this toggle button up here, and then the camera switches to the side, and then I can interact with the Y and Z axis only. So this is a way of us ensuring that people don't get completely lost within the 3D world and not being able to correctly position their 3D slices. The current version of the registration user interface is what was released in September 2019, just before we had the meeting at Stanford. This is currently a prototype. As you can see, it was designed in Unity. We are planning to implement it with 3JS and AngularJS going forward. However, it is accessible online. So again, the reason why we do this is it allows us to generate metadata for 3-dimensional position, size, and rotation of a tissue slice, so that you don't have to write those things down manually. On the second screen, which I didn't show here, you can then copy the data as a JSON file and paste it into wherever you need your data downstream. So this was also a learning process for us in trying to understand how are the systems currently being used. If you are in a surgery room, what kind of systems are in place that we have to tap into going forward? So one of the thoughts, one more thing. So here you can actually see this is the original kidney, and this is the slice that they cut out, that they had to register. And so this is actually the registration that they gave us. And this is coming from Washington University in St. Louis, from the med school there. So we actually had a extended Zoom conversation with them where we went over this particular registration that they did, or this particular surgery that they did, and then we registered this piece for them, just to find out if we can generate all of the metadata that is necessary for this particular surgery. So as we were doing this, we realized that three-dimensional alignment in two-dimensional spaces is obviously very challenging, especially for novice users. We consider all of our users of the system novice users. Why don't we use VR? In VR, alignment of 3D becomes pretty much second nature to our innate human perception. Okay, so VR makes 3D alignment a lot more intuitive than on a two-dimensional screen using a mouse. So what I want to show you now is we modeled a very simple, as you can see, it's like about as simple as you can get. We modeled a very simple alignment task in Unity, and then we piped that through an HTC Vive with SteamVR. And we also recorded a bunch of data of headset movement, controller movement, and so on. So the task was to take cylinder A, move it, and move it into the position of cylinder B, which is an easy enough task. Oftentimes in visualization research, it is very important to go for tests that are as simple as possible to kind of avoid as many confounding variables as you can. Plus, it gives us data that we can actually work through in a reasonable time afterwards. So what we measured is we measured the time and the time that it takes people to complete the task and the distance between cylinder A and cylinder B. The task is recorded as complete when the distance between A and B is less than 0.05 scene units, which would be 5 centimeters. So all of this is like, it's Unity, all the scene units are in English. This cylinder was probably about this big when you were in VR. So it had to be 5 centimeters, is relatively short. So it had to be pretty close and relatively exact to the cylinder. So this is what the task actually looked like. You had your controller here, grabbed your colored sliver, put it over here, and you had to slowly fit it into the cylinder, and then the cylinder would turn green, which you don't see. This is actually a collection of an informal user study that we did in our lab, which was a lot of fun to do and also very enlightening. You can see that the average, this red line here is the average. So we have the duration it takes people to complete the task, and then we have people down here. It shows us that the average duration it took people was about a minute. I would assume the median is probably a little bit lower than that. Our hypothesis, or my hypothesis, without being able to prove that because we don't have the data yet, is that previous exposure to VR, in addition to age, determined the task completion time. So we can, if we like plotted the age and the time it took people, we will probably see a correlation there. But it's probably the previous exposure to VR that makes those kind of tasks a lot easier for people that have been in VR before. I think we can also show this by looking at this graphic specifically. So on the x-axis, we see the elapsed time. So 0 is the starting point of the task. That's when we start the Unity application. And then the elapsed time ends, or the experiment ends whenever the task is done, whenever the task is being fulfilled. Here we only plotted data for 5 participants. So that is myself. Since I actually designed the task, you can see that the time it takes for me to start the application and then grab the piece and actually move it closer to the target cylinder is very short. Okay. So again, this is the distance between the two cylinders. The same is true here for blue is Gagan. Gagan is a colleague of mine. He actually worked for the ABL before, I think, and he has extensive experience with VR also. So you see for him, it takes him only slightly longer to kind of orient himself in VR, and then being able to grab the sliver and move it closer. He backs off for a second, and then he gets close again. So it's really this initial time that it takes people to orient themselves in VR, understand, okay, these are my controllers. I can actually look around, I can walk around. And then the task itself actually goes relatively fast. Katie here, she actually grabbed the piece and she seemed to kind of walk away at first. You see how the distance actually increases. But then once she gets a hold of herself, you see how fast it actually goes to complete the task. Then we have Bruce here, who had very little VR experience before. And Bruce takes even longer to actually understand, you know, how to use the headset, how to use the controllers, and how to just be in VR, which is, I think, something that over time, as people get more and more exposed to VR, should actually kind of solve itself. And then we see he grabs the piece and then he drops it again, and then he just kind of like seems super determined to finish the task, and then he finishes it promptly. And then Charlotte, she had a little bit of our time. This was her first time in VR also. So you can see it takes her about 1.5 minutes to just kind of get the hang of it, understand how she has to look, understand how she has to use the controls, and so on and so forth. And then the test itself takes a little bit longer. So those kind of line graphs were really interesting for us to see in terms of what does people's previous experience with VR tell us about the time it takes to complete those tasks. In my PhD, I'm actually planning to use similar tasks, short ones, to measure the data visualization literacy of people. So I want to close out with just a few thoughts on data visualization literacy and visualization frameworks. There is a sprawling zoo of data visualizations out there. Data visualization is being more and more embraced by the news media, for example, and many frameworks have been proposed to actually capture the sprawling zoo of the more than 500 plus types of different visualizations. Those visualization frameworks also provide guidance when designing data visualizations and teaching them. Now, most of these visualization frameworks are squarely in the area of two-dimensional visualization. So we can see a dot chart here, we have arc graphs, tree maps, all of these really beautiful visualizations that are amazing if your data is inherently two-dimensional or can be represented in two-dimensional space. It's kind of a truism in data visualization that you should only visualize data in 3D if the data is inherently already 3D. So many of these frameworks, in my opinion, don't accurately capture 3D visualization, and especially not visualizations in VR. So I want to just throw out a few points, kind of as an outlook for immersive data visualization. If you Google virtual reality data visualization, this is the kind of stuff that you see. So there are a few things that actually immediately pop out to me. One is, so we have this kind of semi-two-dimensional space here. We see those scales here, and for some reason those scales seem to be really oddly aligned down here, which just doesn't seem right. Then we have the issue, if I wanted to look at this in an actual VR headset, and I would try to use this axis down here, it would probably not make a lot of sense, because if I stand over here and I look down there, it would be very hard for me to tell where exactly are these two balls, for example, aligned. And if I stand over here and I want to understand this visualization, I could not tell at all because of the depth perception here. Then up here on the right, we have this kind of user interface hanging up there, this drop-down menu. Using a user interface in VR, as we know, is very different from using it with a mouse. If you're using it with a mouse, you have a screen-fixed UI that is always fixed to the side of your screen. You always know where to find it. If you're in VR, you either can have it hover over your controller, which is very hard to understand for novice users. If you ever use Tilt Brush, and Tilt Brush actually has a really beautiful way of solving that problem. But you need experience in order to actually use that in a meaningful way. So kind of like beating the simplicity of a mouse interface with screen-fixed UI elements is quite a challenge. And then finally, there is no legend in this visualization. If this were an actual visualization, I think it would be a really bad one, because you need to have a legend, else those colors or the size don't make any sense. And that's another challenge in VR. Adding screen-fixed elements in VR, like always having something hover at the side of your view, really takes away from the VR and from the immersive experience. So you would have to have a UI element that is either intelligent enough to understand when you need it, or you need to have a very smart way of actually making those pop-ups come up. And then you have the challenge of resolution. So especially on like older systems like the Vive, the resolution is so low. If you have like a bunch of secondary screens or UI elements or displays in there, they can be very hard to read. You know, if the graphics that you're using are getting small enough. So there are a few challenges I see for data visualization in VR going forward. One is still the bulkiness of VR. I mean, we've come like a long, long way from the mechanical setups of the 80s, but still using VR is still a chore. You still have to set up your tracking stations. You still need like a really powerful machine. There are headsets like the Oculus Quest out now, which is a great development. I think it takes away from the bulkiness of VR as a whole. Second point is we are very comfortable with 2D spaces. We've all grown up with computers, we've all grown up with mice, and we inherently understand by now how to read two-dimensional screens. There's plenty of real-world research from 2 decades of internet usage about how to design, for example, how to display the results of a search engine. And so this leads to a comfort with 2D spaces that we just don't have for 3D spaces yet. Then again, there are perceptual challenges with data in 3D, as I showed here. It is just simply not possible to read this graph from this location that we are looking at. Because we have this depth perception with 3-dimensional data that we simply don't have with 2-dimensional data. I think the usage scenarios for immersive data visualization in VR have to be appropriate. There's a lot of buzz going on about using VR like to feel data or to hear data or be like surrounded by data in a world of data. And I just don't know if that is appropriate for all usage scenarios. And it might actually lead to a complete overstimulation of your system when you try to understand the data visualization. One of the beauties of data visualization, in my opinion, is the simplicity. The idea is to reduce complexity and map it to something that we inherently understand through our visual perception system. So to summarize, I think it is important to only use 3D visualization, again, for data that is inherently spatial. And then to finish this presentation, almost right on time, we offer a visual analytics certificate in our lab. I'm happy to talk about that later. It is designed for working people, where we talk a little bit more about the theory and the practice of what I showed you earlier. All right, thank you so much for your attention.
All right, if anybody has, we have a couple minutes for questions. If anybody has questions, we have the microphone that Emma Jane is getting. Over here, Emma Jane. Two, one there, one there.
My question would be, what advantage do you think VR can have in visualization of data? But the way we're showing to me might think, when you place someone in the VR, you are basically removing that person from the real world. And I don't know if data visualization justify removing from the real world. Would you consider using AR instead of VR?
We thought about AR before. I've seen some really nice molecular AR visualizations using the HoloLens. But there again, molecules are a data structure that is inherently 3-dimensional already. I don't really see a big functional difference between using a HoloLens for molecular visualization and a VR headset, other than it might be a little bit more safe. Like, we definitely had a few people run into chairs when we did it in our office. I think one of the beauties of VR visualizations over AR is that you have absolute and complete freedom about anything that the user sees. You can basically blend out everything that is happening around them. And so I think you can remove elements of distraction and just have complete freedom over the visual field. And I think that is a huge advantage. You don't rely on the world as a base map anymore. Basically, the way AR works is it uses the real world as a base map or as a substrate and then puts something on top of that. In VR, you don't have that problem anymore. you can create any scale that you want, and you're not reliant on any kind of outside scaling, which I think I think offers a lot of advantages.
Can I complete it?
Yeah, one more question.
Oh, sorry. We can discuss it a little bit later.
Okay, thank you for the nice talk. I wanted to follow up on the last comment you had in the slide. Somehow we've got conditioned to 2D space. Right? We experienced 3D world, but we've got conditioned to looking at 2D. How do you see going forward? Is there a set of training exercises we can recondition ourselves to?
I mean, for like 20 years now, we had 3D video games. I firmly think that video games and video game companies were very early in figuring out how we can navigate 3D spaces. They had to, because they wanted to sell video games. I recently listened to a podcast with John Carmack, who's the founder of ID Software. Like, he created Quake and Doom, and he's now the CTO of Oculus. And those people, like from the early days on, they had to figure out, hey, how can we actually make 3D experiences meaningful? How can we help users accomplish what they want to accomplish in 3D spaces? And so the kind of commercial 3D experiences that we have, I think, give us a really good idea of what kind of interfaces we can have and we can create in VR as well.
Thank you.
Thank you.
Andreas, one last question.
Yeah.
You mentioned the simplification of data to make it easier. Can you describe a little the process that you might go through to simplify data?
Okay, so most data comes in a tabular format, right? So you have a whole bunch of columns with data variables in them. And so when you visualize a data set, let's say with a scatter plot, you have a set of what we call marks and channels, or graphic variables and graphic symbols. So for example, you can have an X and a Y position for 2 of the columns. And then you can encode something else with the size of a dot, and something else you can encode with the color of a dot or with the shape. And so you take all of these data points and you encode them visually. And then suddenly, instead of having to read through a table, which is a terrible form of data representation, we can actually look at something that has the potential to be beautiful. At least it can be visually appealing, and it can convey a lot of meaning in a very, very short time. So we reduce the complexity of tabular representation and make it visual, which humans are inherently better at understanding. I had a chat recently with Mark Smith, who created NodeXL, where he was like, the beautiful thing about data visualization is it's for humans exclusively. Machines don't need data visualization. Data visualizations are there to keep humans in the loop of everything that we do with computers. And I think that was a very beautiful statement. So I think we need this complexity reduction in order to kind of stay in the loop.
All right, great. Thank you, Andreas.
Thank you.